Greetings of the day, dear learners. In this video module, we will learn about the Fourier analysis of scattering in crystals. A crystal is a regular and periodic arrangement of atoms. By this statement, what we means, imagine yourself inside a crystal at the position R. Now you look around the crystal and you observe a pattern. Now translate yourself into another position R plus T with the help of crystal translation vector, that is T is equal to U1 A1 plus U2 A2 plus U3 A3. And again you look around the crystal and observe your pattern. If the patterns you observe at positions R and R plus T is similar, then the crystal is periodic. So the crystal means periodic. Now to map the crystal infinitely into all directions, we need the crystal unit cell that is constructed using the lattice vectors A1, A2, A3. How will you define or understand or identify the unit cell? So will the visible light help us in this case? No, visible light cannot help us to look into the crystal directly because our eye's comprehending power is limited to 4000 angstrom to 6000 angstrom of electromagnetic radiation, that is the visible light, but the crystal dimensions are in the range of nanometers. So whether optical microscopes help us in this case? No, because the optical microscopes are also in the range of micrometers, so it is not also going to help us. So we move on to the higher energy end of electromagnetic spectrum, that is the X-rays. Can we construct an X-ray microscope? No. Why no means no lenses are invented till date that are able to refract the X-rays. So what we can do to understand the crystal or identify its unit cell? So X-rays are going to be interacted, so interacting with the crystals through scattering or diffraction, and we obtain a diffraction pattern, and with the help of diffraction pattern we do some mathematics or physics to understand the crystal structure or crystal parameters. That mathematics is what we are saying the Fourier analysis. So our main objective of this lecture is going to understand the mathematical and physical link of the diffraction, angular diffraction intensities and the electron density in the crystal. So the overview of our lecture will be seeing or understanding electron density rho of R as the source of scattering, then doing the coherent integral summation, then doing the Fourier transform equation, and then constructing the crystal structure from the diffraction pattern. Our diffraction pattern will look like this only, that is the alternate bright or dark spots. So what is the wave electron interaction? That is a wave and the X-ray wave and the electron interactions. We know the X-rays are high energy electromagnetic radiations. Now the magnetic component or the magnetic field component of the X-rays will not interact with the crystal. Only the electric field component of the X-rays will interact with the electron density in the crystals. Now what is electron density? Imagine a NaCl crystal, a one-dimensional NaCl crystal. So we have Na plus ion, Cl minus ion, Na plus ions and Cl minus ions repeating infinitely in space. Now Na plus ions will have 10 electrons, Cl minus ions will have 5 electrons. So what's our case? 10 electron, 5 electron, 10, 5, 10, 5, it is going to be repeated infinitely. So that is the electron density. Now when X-rays incident on these electrons, each electron will act as a secondary emitter. So each electron acts as a dynamic receiver. It receives the X-rays. The X-rays force the electrons into oscillations. When electron oscillates, it becomes secondary emitter and scatters X-rays in all directions. That is the wave electron interactions happen, that the X-ray and electron interaction happening. Okay, imagine a crystal and imagine or consider a small elemental volume dV inside the crystal. When the X-rays interact with this elemental volume dV, the electron density inside the elemental volume dV will scatter the X-rays in different directions. That scattered X-rays will be interfered constructively or destructively and contributes to a smaller part of scattering amplitude. To get a total scattering amplitude from all the elemental volumes dV, we have to do a coherent integration. So that is f of q is equal to integral of rho of r into e power minus iq dot r fq bar. Here f of q is the total scattering amplitude and rho of r is the electron density at the position r or at the elemental volume dV, and e power minus iq dot r is the plane wave representation of the scattered wave. Okay. Now what we understand, there is an elemental volume dV inside the crystal. X-rays interact with this dV, and each dV contributes to one scattered wave and a small part of scattering amplitude. All the summation, all the contributions of the elemental volume will add up together to contribute to the total scattering amplitude. Now comes the periodic electron density. Again, earlier we consider the case of NaCl ionic crystals. So we understand electron density as a periodic function, right? So any periodic function can be represented as a Fourier series. Here we have to understand Fourier series intuitively, then only we can understand how this periodic electron density comes to the Fourier analysis, right? What is Fourier series? For example, consider a periodic wave of 100 Hz. Now, what Fourier says means an infinite number of sine waves and cosine waves of different frequencies, different amplitude and different phase can be added together to obtain that periodic frequency 100 Hz. Imagine, I would say, if you add a sine wave of 10 sine waves of 90 Hz frequency and a particular phase, and then add 5 sine waves of frequency 1000 Hz, and then add 3 sine waves of 10 Hz, and again add 20 cosine waves of frequency 50 Hz, and 5 cosine waves of frequency 2 Hz, and 2 cosine waves of frequency 10 Hz. Then all these 6 sine and 3 sine waves and 3 cosine waves will form the periodic function, that's a frequency 100 Hz. Now each I am saying 10, 5, 2, that number is the Fourier coefficients, what we say an, bn. So we all know Fourier series is a naught plus integration of a naught sin n of x and bn of sin n of x, right? That a naught, an and bn are the weightage of particular sine wave in that construction of periodic wave function. So what we say, there are going to be a definite number of sine waves, definite number of cosine waves that are going to be added together and form a periodic function. So the Fourier coefficient will tell you the weightage of that particular sine wave in the periodic functions. Now come to our case. Electron density is a periodic function, that is rho of r is a periodic function, and we can represent that electron density as a Fourier series. Now in the crystal case, not all the sine waves or not all the cosine waves are allowed in the series. Only certain frequencies, certain spatial frequencies that is compatible with the periodicity of the crystal is only allowed. So restriction, how will we restrict the certain number of sine waves and cosine waves from entering into the series means, consider this figure. Here we are representing the crystals as crystal spacing A. Okay. Now take one sine component and fit the sine wave into the crystal. Here at a particular crystal spacing, take as a case of a by 2, take the case of a by 2. In the first sine wave at the position of a by 2, the crystal sees a peak amplitude at 90 degree phase. When you look into all the crystal spacing at all a by 2, the phase at the phase 90 degree, the amplitude will be peak amplitude. And take the second wave. Here at all the positions a by 2, at the phase 90 degree, the amplitude is 0. That means the waves are allowed. Now take the third case. Here at the position a by 2, at 90 degree phase, we have different amplitudes. That means that wave is not allowed. So for a particular sine or cosine component to be allowed in the Fourier series of electron density representation, that particular sine wave must fit exactly into the crystal. That means the crystal should see equal spacing or similar phase of the sine wave. So any periodic wave function can be represented as a Fourier series. Our electron density is a periodic function and we are going to represent the electron density as a periodic function. Again, we understand that all the sine or cosine components are not allowed, only certain frequencies are allowed. So that certain frequencies or certain wave vectors forms the reciprocal space or reciprocal lattice of the crystal. Here for a crystal we have a real lattice and a reciprocal lattice. When you compare real lattice and reciprocal lattice, here inside a real lattice we define positions, whereas in reciprocal lattice we define spatial frequencies. The real lattice contains electronic charge distribution, continuous electronic charge distribution, whereas the reciprocal lattice contains allowed periodic, a library of allowed periodic wave patterns. Here the real lattice, in the real lattice the unit is measured in length, whereas in reciprocal lattice the unit is measured in inverse length. So the electron periodic density rho of r is now expressed as the Fourier series summation over G Ng exponential I G dot r. Here G's are the allowed wave vectors inside the Fourier series. G's are the allowed wave vectors of the Fourier series, and Ng is the Fourier coefficient, that is the weightage of the particular wave vector G in the Fourier series. Now we are going to substitute this form of electron density rho of r inside the total scattering amplitude equation, that is the f of q. Now you get the equation integral of Ng exponential I G dot r into exponential minus IQ dot r into FQ bar. Here when you look carefully into the equation, you can understand that when Q is equal to G, the exponential will cancel out. That means the waves will interfere constructively and you get a bright spot. When the exponential becomes 0, e power 0, it will give you the value 1, and beautifully the scattering amplitude f of q becomes the Fourier coefficient Ng. So this is the case. Now the electron density becomes the Fourier coefficient. So the mapping of Fourier space in the detector screen. In the detector screen, each pixel corresponds to a particular scattering direction or particular diffraction direction. When you get a bright spot inside a pixel means the Fourier coefficient is large. When you get a spot but the intensity is low means the Fourier coefficient is small. So inside a detector screen you get bright or dark spots in all pixel spots, and all the pixel spots corresponds to one particular scattering direction, and each bright or dark spots inside the pixel will give you the Fourier coefficient of all the components. When you get the Fourier components of all the scattering direction, you can construct the electron density. When you construct the electron density, you can do inverse transform, inverse Fourier transform, and you can get a mapping of reciprocal space. That means the detector is nothing but the mapping of reciprocal space, and using that reciprocal lattice vectors and the relation of reciprocal and real lattice vector, you can construct a real lattice, and with the help of real lattice you can define your unit cell, you can define the translation vector, and you can map the entire crystal. Hope this video module helps you in intuitive understanding of Fourier analysis and the scattering amplitude. Thank you all.